Okay, in this video, we're going to be actually going through an application of design. We've talked a lot about small scale integrated circuits, medium scale devices, and we're going to look back a little bit at how we use a K-map to actually do a design, and then see how this is implemented with some more current technology. So we're going to look at kind of a basic application. In this case, we're going to create a decoder. And a decoder is going to take some binary inputs here, call them A, B, C, and D, and decode an output to drive an LED display. So in this case, we're going to be looking at a 7-segment LED display. All the way to 7. So this is the basic device that we're going to be looking at. So the reason it's called a 7-segment display or LED display is if you take a look up at the picture here, this shows you all these different segments, which represent either individual or groups of LEDs. They're labeled, the standard labeling for these is A, B, C, D, E, F, and G, as you go kind of in a clockwise circle there. So for example, if we wanted just to display the number 0, we would turn on segments A, B, C, D, E, and F and leave G off. Now, what you're seeing here on the top is a truth table for all of these different individual segments. And that would be the case over here where all the 4 inputs would be 0 or low. So the truth table shows which segments are turned on, for example, to display a 0. And in that case over here, those would be those 4 inputs, all 0. So let's focus just on the A segment. We're going to basically decode all of these 4 binary inputs that are over here in the little drawing and use it to decode the outputs to drive just that segment. Now that's shown here in the column, okay, for the numbers 0 through 9. So what I've done here is I've taken all these values, the 1, 0, 1, 1, etc., and copied them over here to the left. Now, we could decode this to make some kind of quasi-hexadecimal display. You can actually create these other letters, but all we're interested really in are the 0 through 9 numbers. So these other ones are going to be basically don't cares. So let's take a look at how this process works. Okay, what we're going to do is take a look, erase those there. We're going to take a look at the inputs and fill our K-map with these values. Again, the K-map, all it is a method of decoding or reducing the Boolean logic down to the simplest number of gates. So for these 4 inputs, 0, 0, 0, 0, we have a 1. And so in the K-map, 0, 0, 0, 0, all those inputs are 0. I'm going to write a 1 here. And by the way, I didn't write this up here, but these are inputs A, B, C, and D. And that's what we're mapping there. Okay, let's take a look at the next one. 0, 0, 0, 1 is a 0. So we have 0, 0, 0, 1. That's going to be a 0 there. 0, 0, 1, 0 is a 1. 0, 0, 1, 0 is a 1. And 0, 0, 1, 1 is also a 1, which is this one right here. Okay, we've done K-maps before, so I'm going to go ahead and populate this with the rest of these values. Okay, so I've populated all the values up to 9 here. Okay, but for the rest of these are don't cares. So traditionally, we just write in X's there. But because we're grouping all the 1s, what we can do is simply fill in all the rest of these values with 1s, which represent all of these X's, A through F. So I'm going to go ahead and fill those in. So the next step we're going to do is grouping all the maximum number of terms together. And I'm just going to flip over now to the display or the whiteboard so you can see this a little bit better. So if we look closely here, we can see we have 8 1s grouped together. A lot of those are the don't cares. So I'm going to combine all those together, and that will be a single term. Okay? And that makes it actually easy because that kind of makes our circuit a little bit more straightforward. So to determine what that value is, let's take a look at these values going up and down and left and right. So up and down, A is a 1, and it doesn't change, so we know we have A there. However, B transitions from 1 to 0, so we'd throw that out. And because as we go across these rows here, all of these columns are individual values that are different, so that term ends up just being A. Okay, and we're going to OR that with a couple other terms here. So the next one that we can identify that has 4, okay, and there are multiple ways to do this, but this is just one example. But I can see that these 4 terms in the middle can also be grouped together. And it doesn't matter that they're crossing over. We'll see actually what happens with that, but that's okay. We're trying to get the largest number of terms. So in this case, A is transitioning from 0 to 1, so it's a don't care. B is a 1, though, as we go from this row to this row. So we have B. And let's see what happens here. As we go from this row to this row, C transitions from 0 to 1, but D is a 1. So we have BD as being that term. Now, there's another grouping of 4, if you look carefully, which is kind of the weird one, where if we look in the 4 corners, we can group those 4 together. Now, when we do that, let's take a look at what we end up with. So if we go from this column to this column, we have A is 1, B is 0, okay, and that doesn't change all the way across. The tricky thing about this one, however, is we can't ignore the other ones that are not included here. So let's take a look at what we really have. Here we have B naught, and we have B naught, and B naught, and B naught. But if we go from this column to this, or this row to this row, we'll see that A changes. So we end up with B naught. And let's take a look at the other possibility. C, if we go from this column to this column, C changes, but D is still 0 there, and it's the same down here. So we end up with B naught, D naught. Now, we can still do one more grouping here. We've got these 4 grouped, the middle 4, the outside. We can also get this set here. And yes, there's a lot of overlapping, but that's okay because that eliminates extra terms. So what does that column look like? Well, if we're looking at these 4 going up and down, A and B are changing every time. So we have to throw those out. But in that column, C is 1 and D is 1. So we can have that as CD. And that's the equation for our circuit. So now let's take a look at what this really means, though. This is saying X, the output for that one segment, the A segment on that LED display, it's just that top one there, can be created by mapping these different inputs here. So if we were to implement this as a circuit, we'd have to draw it something like this. So this would be the implementation of the circuit. Sorry about the glare there. And what I'm doing, I'm kind of taking a little bit of a shortcut here. Instead of drawing the inverters, I'm just showing these as B naught, D naught, but what that would require is an inverter coming into those pins. Now, this type of circuit is referred to as a sum of product. The reason why they call that, or SOP, the reason they call it sum of product is we're summing all the products of these terms. Even though we're not really adding the values, the symbol for the OR gate is the plus sign, and for the AND gates, it's a multiplication symbol. So we're summing all those product terms. Now, like I said before, that little design that we just did is only to control the A segment. You'd actually have to do that for all 7 segments, and then figure out also how to kind of do more reduction. And so when you start to look at that, you realize that a 7-segment decoder is a pretty complicated logic device. But I want to show you something that we haven't really talked about before that's very interesting. If you'll notice, if you haven't noticed already, if you look carefully on this logic map, the K map, there are very few zeros here. And this is what I'm going to kind of refer to as negative space. Maybe you've had an art class where they talk about the area around the image that you're trying to paint as being the negative space. The other way of looking at it is called negative logic. So what's interesting is we can actually create a logic circuit based on the zeros instead of the ones, and sometimes this is a simpler implementation. So this kind of a logic circuit is referred to as POS, which is product of sum. And what that means is that instead of having the AND gates in the beginning, the AND gate is at the end, but we're going to OR sets of terms at the beginning. Now what's kind of weird about this is that instead of looking for a 1 here on the output X, we're actually trying to find, inputs where we only have a 0 on the output. So for example, an AND gate requires both inputs to be 1 to have a true or a 1 output. But if either of these sets of inputs are 0 or one of them is 0, that means the output would be 0. So what we're going to do is kind of design something a little bit what may seem backwards. We're trying to find a situation where we have zeros here, different combinations of zeros, that would then drive a 0 on the output. And that's what we're going to look for at the K-map. So as I go through this, I think it'll make sense, but it's a little bit flipped from what we're used to looking at. So let's take a look at this. We're going to group them the same way we did before. We're going to group these two terms together. Now there aren't too many zeros here, but we can group these two together by doing that kind of fold around grouping. And what would that be? Well, A is 0 and B is 1 for both of those terms. And let's see what else is going on there. So that would be A naught, B, and then going from here to here, C is transitioning, but D is not. D is 0. So we'd write that as A, B, D naught. That would be the first set of zeros. Now the last one, unfortunately, he's all by himself. So we can just map that cell as the A, B, C, D values that we see here at that coordinate or that location. Now, what's interesting though is that we have to be careful here. I'm going to write out the other terms that we have. This would be A, B, A naught, B naught, C naught, and D. But because we're flipping these around, instead of ANDing these together, we're going to actually OR these terms. So I'm going to write this as ORing. A naught, or B, or D naught. And then we're going to AND that with A, or B naught, or C naught, or D. So it's kind of the opposite approach that we've taken, but the reason why is we're trying to solve for where there are zeros here. So if you look at that, if you actually plug in the values, for these inputs, for example, 0, 1, 0 for A, B, and D, that would drive an output to 0. So what does that circuit look like? So the way the circuit is implemented, and sorry my writing here isn't terribly great, but these are OR gates that we're looking at. And we're ANDing those together. So it's a product of two sums. And what we're looking at here again is where X is driven to 0 based on the input combinations. So this is called POS, kind of a little bit trippy, but it can be implemented also using these same types of logic gates.